In this video, we are going to solve some problems based on moment of inertia or rotational inertia. So let's see what's the first problem. The figures show three different systems. So we have got three different systems here, each consisting of two massive spheres connected by rods of negligible mass. So the rods themselves, they don't have any mass, only the spheres have the mass. In system 1, each sphere has a mass of 2m0 and is a distance d0 from the axis of rotation. So this is our axis of rotation and there are two spheres here. In system 2 and 3, each sphere has a mass of m0 and is a distance 2d0 from the axis of rotation. Okay. The sizes of all spheres are small compared to d0. How do the rotational inertias I1, I2, I3 of the three systems compare? So you want to find what's the rotational inertia for each system. So for that, we will be using the formula for rotational inertia for a particle, point particle rotating at some distance away from the axis. So that formula is I is equal to mr square. Let's write it as sigma mr square because we have got here multiple masses. So for system 1, we have got two masses and they both are at a distance of d0 from the axis of rotation. So I for the first system will be 2m0, which is the mass of one of the spheres, multiplied by d0 square. So we got the rotational inertia for one sphere. We have to repeat it because there are two of them. So the same rotational inertia because they have the same mass and the same distance. So this will be 4m0 d0 square. That's for system 1. Now let's do it for system 2. So for system 2, again I2 will be m0. This time the mass is only m0. The distance is 2d0 square. So remember that the distance from the axis of rotation is being squared in the formula. So plus, we repeat that, there are two masses, 2d0 square. So this will be m0 4d0 square plus m0 4d0 square. When we add it, 4 plus 4 will give us 8m0 d0 square. Now for system 3, let's do it here, system 3. Now remember that it does not matter how the system is looks like. When you look at the picture, you see system 2 and system 3, they look different, but the distance is same and the masses is also same. So it will be the same moment of inertia. So let's just write it and do it again. m0 2d0 square plus m0 2d0 square. There are two masses, we can see that, and their distance is 2d0 from the axis of rotation. So when you solve this, this will also come out as 8m0 d0 square. So what we find is I2 and I3 are equal to each other and obviously they are greater than I1. So I2 should be equal to I3 and they both are greater than I1. Let's see if we have anything like that. Yes, it's C. So the answer is C here. Next, we have got one more problem on rotational inertia. So we have got three systems again. The figure shows three systems, each consisting of rod of negligible mass, one mass and one or two spheres attached to the rod. Each system can rotate about an axis that is perpendicular to the plane of the figure, located at the left of the rod, and each sphere's mass is either m0 or m04 as indicated. If the rotational inertia of each sphere about its center of mass is negligible, which system, if any, has the greatest rotational inertia? So the same process we'll repeat. So for system A, we have got only one mass here. We can see this is the axis and the distance is d0. So I equal, so the formula is I equal sigma m r square. So because there is only one mass, we can do it just for one mass, m0 d0 square. And that is for system A. For system B, there are two masses, but one of the mass is on the axis itself, so it does not have any distance. Its distance from the axis is 0, so its rotational inertia will also be 0. So we are left with only one mass, which is similar to what we have in system A. So that will also be m0 d0 square. The system C, we have got one mass and the distance is given to us, so let's just do that. IC equal m0 over 4 multiplied by 20 square, m0 over 4 multiplied by 4 d0 square. 4 and 4 gets cancelled. I get m0 d0 square. We can see that all the moment of inertias are equal to each other, so all of them are having, and we have that option here, all three systems have same rotational inertia.